let's now talk about one of my favorite subjects, dimension reduction. And in particular, let's start with a discussion of the curse of dimensionality. Now, you may have heard this phrase floating about the internet, but we're going to get a concrete look at what exactly it is. Now, as the dimensionality, that's the number of variables, of a space grows, data points become so spread out that the ideas of distance and density become murky. And this is simply due to the incredible spatial increase that comes from adding each additional dimension. Let's first think about that. We'll do that. Let's just pretend that you are a point and you have infinite potential energy just bursting at the seams with potential movement. But if you live in zero space, you sit at the origin, there is nowhere for you to move. Now imagine that suddenly you're given a dimension. Oh, the joy of movement as you move along that dimension, whee, back and forth, out towards infinity on either side, and back and forth. And, compared to your previous existence, the world seems infinitely more expansive. And now we're going to level up. Here comes another dimension. That's in the form of another basis vector, another axis. Oh man, whoa, I can go anywhere. It's just really a lot of space. I never imagined so much space. We couldn't possibly imagine a third dimension. Being able to move off the computer screen, back and forth to infinity. The amount of additional space that you're adding in each dimension actually seems to get larger, right? When I went from one line, one-dimensional space, to a plane, two-dimensional space, it's like I had infinitely many more lines to move along. But when I add the third dimension, what I actually get is infinitely many more planes to move upon. And when I add the fourth dimension, it's like infinitely many more 3 dimensions to move upon. And so every time you add dimensionality to the space, the volume of the space grows much, much faster than the dimension. We can expand this more concretely in a way that we can actually put our finger on exactly what's happening. Well, sort of. By just envisioning some data in 2 dimensions. So here I have randomly generated points. Of course, some of those points are close together, others are far apart. And what I want to do is look at the ratio of that maximum distance to the minimum distance. It turns out the maximum distance in this picture is 30. The minimum distance is 0.02. So the ratio of the maximum distance to the minimum distance is 30 over 0.02, which is 1500. Okay, so the way we interpret that is that the max distance is 1500 times larger than the minimum distance. Well, that doesn't seem groundbreaking, but what we're going to do is generate those 500 points in 3 space, in 4 space, and all the way up to 500 space. And we're going to compute that same metric, the ratio of the maximum distance between points to the minimum distance. And we're going to observe the behavior of that ratio as the number of dimensions grow. Here's a plot. On the x-axis, I have the dimension of the space. Here, I'm only going up to 50 dimensions. And on the y-axis, I have that ratio of the max distance to min distance. And you recall in my earlier example, we were somewhere around 1500. The data I generated here had a ratio of above 3000. But as I increase the dimensionality of the space, that ratio quickly decreases, even though the points are generated in exactly the same fashion. Now, because this decreases so quickly and it looks like the ratio is going to 1, this green line is drawn at y equals 1. What I'm going to do is I'm going to take the log of this ratio, just so I can see the behavior down here a little bit better. But the conclusion that you should draw from looking at it is, wow, it looks like the ratio goes to 1, which means that the max distance would be equal to the min distance. That's weird. So here's the log. Now you'll recall that the log of 1 is equal to 0. So as this line approaches 0, we have the max distance approaching the min distance. And when we go out to 50 dimensions, you know, we're not there yet. This is asymptotic. We will never actually reach it. But that's where it's going, which is really quite remarkable. That as the dimension grows to infinity, the max distance becomes the minimum distance. The distribution of distance becomes nearly constant. All the points become equidistant, even though they are randomly generated in the same way that two-dimensional scatter plot was. Here's another way we can look at this. We can look at a sphere that's inscribed in a cube. When I say it's inscribed, I mean that the sphere is touching the cube on its 6 sides, these dots. Okay, and we're going to assume that this is a unit cube, meaning that the length of each side is 1, and a unit diameter sphere, meaning, of course, that the diameter would also be 1. Now, here's some math that you may or may not know. It doesn't matter if you know it. I'm just going to give you the formulas. But the volume of a sphere is 4/3 times pi times the radius cubed. Of course, if the diameter is 1, the radius is 0.5. So the volume of a sphere is 0.52. The volume of a cube is 1. Length times width times height. So the sphere here takes up over half the space. There's still a good bit of space in the corners. Now, in d-dimensional space, the volume of a hypersphere is composed, if you want to think about what a hypersphere would be in d-dimensional space, you could think about the unit hypersphere just being all points that have length 1, meaning that they are 1 unit away from the origin. That would carve out a sphere. All right, there's a formula for the volume of a hypersphere. I certainly wouldn't expect you to know this, but it is 2 times the radius to the dth power times a pi to the d over 2, and then you have a d in the denominator and a gamma function of d over 2. Now, the gamma function is whatever this is, minus 1 factorial, but again, doesn't really matter right here. Okay, and the volume of a hypercube will always be whatever the length of its side is to the dth power. Now, of course, this is 1 to the d, so it's just 1 for the unit hypercube. Now, what's amazing about this is that if we look at the limit as the dimensions grow of the sphere volume to the cube volume, we get 0. The volume of that unit hypersphere compared to the cube volume is going to go to 0. There's comparatively no volume in the sphere. And it's like all the volume of the hypercube is contained in the corners. That's really bizarre. And no distance or similarity metric is immune to that vastness of high dimensional space. We can look at one more. We'll look at the distribution, or lack thereof, of cosine similarity. If we compute the cosine similarity between each pair of points and observe the distribution of that value as the space grows, this is what we'll see. In 2 dimensions, I get some points that are highly collinear. They're close together from an angular standpoint. As I grow to just 10 dimensions, I start to get a very different distribution. And in 50 dimensions, 100, 250, by the time I get to 500 dimensions, the cosine value is very narrowly distributed around 0. It's like everything is orthogonal to each other. Now that's only 500 points. That's 1 point for each dimension. But even if I increase this sample size to 10,000, my distribution does not change very much from this. The distribution gets a little bit wider because technically, if you have enough points to fill the space, the dimensionality is not such an issue. But as you increase dimensions, the number of points you have to increase grows. And so even if I increase from 500 to 10,000, I still have a distribution that looks very much like this. It's not nearly as wide as this one here. And so that really shows us the point here is that it's hard to use distances in high dimensional space. Now, when is this a problem? Primarily when using algorithms that rely on distance or similarity. Now, that would mean clustering and nearest neighbor methods could really fall apart in a high dimensional space. But really on any model, due to the collinearity and a desire for model simplicity and computational efficiency. Predictive models, any kind of predictive model, will usually suffer from high variance, which means overfitting, in high dimensional data. And the computational load can be greatly reduced in many scenarios through dimension reduction.